All right. Oh, score my eyes.
Get huge savings on the hottest.
In classical Newtonian physics, the Lagrangian of a system is the total kinetic energy minus the total potential energy. In classical Newtonian physics, the Lagrangian of a system is the total kinetic energy minus the total potential energy. In quantum field theory, this simple relationship is no longer true, and the equation for the Lagrangian at each point in time is a function of all the fields throughout all of space. We could be dealing with Einstein's theory of relativity, or with quantum field theory, or with Newton's laws of motion. When physicists propose new fundamental laws of physics, they often do so by proposing a new equation for the Lagrangian. What we therefore want to focus on is not the equation for the Lagrangian in any one specific theory, but how the Lagrangian is used to predict the behavior of a system, as this has universal practical and philosophical importance. Suppose we know the initial state and the final state of a system. We wish to calculate the path between the initial and the final state. The system can consist of any number of fields and particles, and the system can contain any number of independent variables. Here, we just show 3 independent variables, which we will call x, y, and z. Let's just show the variable x. The variable x could refer to the position of a particle along one dimension. In order to calculate the future behavior of a system, we need to know both the position and the velocity. We will refer to the velocity in the x direction using the symbol x with a dot over it. Suppose we have a function that depends on both the position and the velocity. We will call this graph the Lagrangian. The Lagrangian is also a function of all the other independent variables. This graph could also be a function of time. All the equations shown in this video will be valid regardless of whether or not the graph depends on time. For the following animations, we will show a graph that does not change with time. We don't know the path between the initial and final state, but let's propose one possible path as a guess. The height of the red ball at each point in time symbolizes the value of the Lagrangian at each point in time. Here, the color symbolizes the value of the Lagrangian. time is not shown on this graph, but we can change the graph so that it shows the value of the Lagrangian as a function of time.
External worm. Worm type. Ooh.
Let us say that the region in red is considered to have a negative area, and the region in green is considered to have a positive area. The total area is what we will refer to as the action. The action is a function of the entire path as a whole. If the path changes, then the action also changes. We can plot this on a graph as shown. Let's consider the slope of this graph at each point. If we are dealing with physical laws where the total work done depends only on the initial and final state of the system, and not on the path in between, then the true actual path of the system must be at a point where the slope of this graph is 0. One place where the slope can be 0 is where the action is at a minimum. For this reason, people often refer to using this method to find the path as the principle of least action. However, a more accurate description would be the principle of stationary action, since the actual path needs to be at a point where the slope of this blue line is 0. To find where this happens, we need to consider the partial derivatives of the Lagrangian. The slope of this line is the partial derivative of the Lagrangian with respect to x. Here, the color represents the partial derivative of the Lagrangian with respect to x. Let's change the color of each ball to match the color of the graph at the ball's location. Let us now view this as a function of time. Let's change the vertical position of each ball based on its color. We now have as a function of time the partial derivative of the Lagrangian with respect to x. This is just one of the partial derivatives we can have. We can also have the partial derivative of the Lagrangian with respect to the variable symbolized by the x with the dot over it, which we will call x dot. Here, The color represents the partial derivative of the Lagrangian with respect to x dot. Let's change the color of each ball to match the color of the graph at the ball's location. Let's view this as a function of time. Let's change the vertical position of each point based on its color.
Biff. Biff.
We now have as a function of time the partial derivative of the Lagrangian with respect to x dot.
Biff.
Let's represent the slope of this function of time with a new set of colors. Let's again change the vertical position of each point based on its new color. We now have this new expression as a function of time.